Welcome back to the STEM Tutor. Today we're going to be discussing cis, trans, E, and Z naming with alkenes. Before we get into naming, let's talk about isomers. Isomers are compounds with the same formula, but different rotations or connections. I will be making a video on stereochemistry later on, but I wanted to focus on geometric isomers. These are compounds that differ in their geometry with respect to a rigid structure, and it usually happens with double bonds or rings. We are going to focus on the double bonds part of this definition, because double bonds, as we know, are alkenes. Cis-trans isomers, and cis-trans also includes E and Z, are geometric isomers. So for example, say we have this 4-carbon chain butane, just a single alkane, and then we have butene, 2-butene, with a double bond on the second carbon. When we draw organic structures on paper, that only accounts for the 2-dimensional portion of the shape. We haven't accounted for the 3-dimensional structure of our shape yet, and that is where stereochemistry and isomers can come into play. If we have this alkane with single bonds, we can rotate our shape around this carbon to get something like this, where this carbon bond is now pointing in this direction, but it would still be called butane because it's a single alkane chain of 4 carbons. Now if we look at 2-butene, if we tried to rotate our shape about this carbon, we would not be able to rotate it. The bonds would be locked in place. If we take a look at this compound, this is also 2-butene. We have 1, 2, 3, 4 carbons here, and we have 1, 2, 3, 4 carbons here, and our double bond is between the carbon 2 and 3. So both of these compounds have the same name, 2-butene or but-2-ene, but they are not the same compound. Although they are numbered the same way and have their double bond in the same place, we would not be able to interchange the shapes by rotating about a bond, even though it looks like we can bring this carbon down here. So these are what would be called geometric isomers, where these compounds have the same atoms connected to one another, and they have the same chemical name, however they differ in their geometry. Note that these double bonds are also called pi bonds. When we name alkenes, we use something called the Kohn-Ingold prelog or CIP system. It comes more into play when we talk about E and Z alkenes, but the rules work the same for cis and trans. Let's look at this simple example. This is a 2-butene. But because we have 4 carbons, ene because it's an alkene, and 2 because the double bond is on the 2. First, I narrowed down whether I'm going to be using E and Z or cis and trans. Although cis and trans can be used in simpler situations, usually we have complex structures and we will have to use E and Z. When the carbons in our double bond, so in this case it's carbon 2 and 3, are tetra-substituted, so right now each carbon is making 3 bonds. Carbon number 2 has 1 bond here and 2 bonds in the double bond, and same with carbon 3. However, if we had different groups coming out of these carbons, they would now be tetra-substituted with 4 substituents on each. In this case, we would have to use E and Z instead of cis and trans. Now that we know when to use them, let's discuss what exactly E, Z, cis, and trans mean. So cis and Z mean same. The bonds on either side of our double bond are going in the same direction. And trans or E means different. I like to remember sisters, because sisters can remind you that cis and Z are the same, and trans and E are different. So let's use the CIP rules on this alkene to name it with cis, trans, E, or Z. So this shape is 2-butene, and I talked about naming alkenes in a previous video, so I won't go through that now. But let's just talk about how we can figure out whether this is an E, Z, cis, or trans bond. The first thing I do is perpendicularly cut my double bond in half. So then I have this side of the bond and this side. Now I like to draw in any invisible hydrogens on my carbons so that I can get a good look at what my priority groups are. If there are no invisible hydrogens, you might have a tetra-substituted shape like this. So first, we ask ourselves, are we going to use cis-trans or E and Z? We usually use E and Z when we have tetra-substituted carbons, like I mentioned before. Here, our carbons in the double bond just have hydrogens coming off of them as the fourth substituent. So we can use cis and trans in this case because it's a very simple alkene. So I'd first look at this carbon in my double bond, and carbon should always be making 4 bonds. 2 of them will be going into the double bond, so we look at these 2 other bonds that are not the double bond, and we compare them. This first bond is a carbon, and this first bond is a hydrogen. Priority is based on atomic number. Carbon has a higher atomic number than hydrogen, therefore carbon is going to be our priority group on this side. Down here we do the same thing. We only have a match between hydrogen and carbon has the higher atomic number. So these are the 2 groups we are comparing on either side of the double bond. And starting from the double bond, we will draw our arrows to see which direction our bonds are going in. So starting from this line here, this bond is going in this direction, this bond is going in this direction. Because they're going in opposite directions, we have a trans. So we would name this as trans-but-2-ene. Let's try looking at the same example, but now it's going to be cis, and I'll explain why. We still have a but-2-ene. We have 4 carbons, and on carbon 2, we have the double bond. So we still have the same compound. However, because the bond is pointing in a different direction, we are now going to have to put a different prefix in front of the name. Now, if we looked at this shape, first we would wonder, do we use cis and trans or E and Z? As you remember from the previous rules, we first cut the double bond in half and draw in any invisible hydrogens on our double bond carbons. In this case, we don't have any tetra-substituted carbons on our double bond. This carbon and this carbon both have hydrogen as the fourth substituent, in which case it's a simple compound that we can use cis and trans for. Now, how do we know whether we are going to use cis or trans? So we need to check the priority of the 2 groups other than the groups in the double bond. So the 2 groups coming out of this carbon are carbon and hydrogen. Carbon is the higher priority because it has a higher atomic number on the periodic table. Same thing with this carbon here. This carbon number 4 has a higher priority than the hydrogen because it has a higher atomic number. Now, parallel to the double bond, I'm going to draw in the direction of each arrow to indicate which direction our bonds are going. And both of them are going in the same direction, which means we have a cis. So this is cis-but-2-ene, and our last shape was trans-but-2-ene. So you can see, although they were both a but-2-ene, they were either cis or trans, and their reactivity in chemistry is going to differ based on this geometry. Now let's do more complicated examples where we need to include an E or a Z. Let's take a look at this example. Remember, the first thing we ask ourselves is, are we going to use cis-trans or EZ? Well, we look at the carbons that make up our double bond, and we see that this carbon here has all 4 bonds as different substituents. There are no hydrogens off of it, although this carbon does have a hydrogen right here. Because this one carbon in the double bond is tetra-substituted, we should use E or Z. Next, we make a perpendicular line down the double bond, and we need to compare the priority groups on either side. The CIP system says that we need to go bond by bond comparing the atomic number to determine the priority of our groups. So remember that we look at the 2 bonds directly coming off this carbon that are not inside the double bond. So these 2 bonds are what we are going to look at. So coming off of our double bond carbon, we have a carbon up here and a carbon down here. Because it's a tie, we need to keep moving forward and go bond by bond until we break that tie and determine the higher priority group. So after this carbon, it is connected to 3 hydrogens. Any carbon that has nothing else on it is just a CH3, a methyl group. But after this carbon, it has those 2 invisible hydrogens there. If you don't see 4 bonds directly on your carbon, and there's a formal charge of 0 on your shape, then assume that the rest of those bonds are filled by hydrogens. So now that I see all 4 bonds this carbon is making, 2 of them are hydrogen, but 1 of them is chlorine. Whereas up here, all 3 bonds are hydrogen. Now this group is going to have higher priority because one of these hydrogens from above has been transformed into a chlorine. And chlorine has a higher atomic weight than hydrogen on the periodic table. Now let's compare the groups on the right-hand side. Coming out of this carbon, we have a hydrogen and an ethyl group with 2 carbons. Carbons have a higher priority than hydrogens, so we don't even need to do the comparison like we did on the left side. So these are the 2 groups we're comparing. Now I draw a line parallel to our double bond and draw the direction of the bonds. This bond is going down, this bond is going up. Therefore, we have an E. Remember, E is when bonds are going in different directions, and we had previously determined that we have to use either E or Z. Now that we know we are using an E, we will name the rest of our shape. So our main chain should include the longest possible chain that includes the double bond. We have 1, 2, 3, 4, 5 carbons here. And on the first carbon, we have a chlorine. So we have 1 chloro. On the second carbon, we have a methyl, and our chain is made up of 5 carbons. Pent, which is the prefix for 5, the double bond is on the 2, ene. So we have E, 1 chloro, 2 methyl, pent, 2 ene. Note that there is no space or dash between the last substituent, which is 2 methyl, and the name of the main chain, pent, 2 ene. Now let's take a look at this example where we have 2 double bonds in the same shape. We had already determined that this previous double bond was an E, but now we have to determine whether this bond is E, Z, cis, or trans. Before we do that, let's name the rest of our shape. So we would start the numbering from the right. So if we started numbering from left to right, our double bonds would still fall on the 2 and 4, but these substituents have lower numbers if we start from the left. So I'm going to start my 1 from down here, and I have a chlorine on the 1, which is a 1 chloro, a methyl on the 2, double bonds on the 2 and 4, and my longest chain is a 6, so it's a hex. Now to put it together in order, we always go in alphabetical order, looking at the first letter of our substituents. So we have the 1 chloro, dash 2 methyl, and hex, 2, 4 because we have 2 double bonds, diene because we have 2 double bonds. Now if I just left an E or a Z in the beginning, how would I know which double bond it's referring to? So we need to put numbers next to them. The double bond on carbon 2 is an E, so we have a 2E, and the double bond on carbon 4 is, we don't know yet. So let's figure that out. So we will first cut the double bond in half perpendicular, and then we will add in any invisible hydrogens, and now we will compare the groups. Looking at the right-hand side, this is the priority group, because up here is hydrogen and down here is carbon. And on the left, the priority group is also everything over here, because up here is just a hydrogen. Now when I draw a line perpendicular to our bond and draw the direction of each of the priority groups, I have both of them going down. So this is going to be a Z. So we have 2E, 4Z, 1 chloro, 2 methyl, hex, 2, 4 diene. Although the carbons on our double bond are not tetrasubstituted, I still used Z instead of cis because the left side of our shape is more complex. I've seen cis and trans used more often when the shape is more symmetrical, like the simpler examples we did earlier. So now that we've covered how to name alkenes using cis, trans, E, and Z, I will leave a link below to the related blog post at my website, thestemtutor.org. Thank you for visiting, and I hope this video helped you. Bye for now.